Welcome to the course on game theory in the autumn term 2020 at the University Mannheim. This is the first video of week 10. We still are in section 5.4 on repeated games. We have discussed finitely often repeated games, and now we come to infinitely often repeated games. So one starts with a game in normal form, and then we look at the infinite repetition with a certain discount rate delta. This new game is called gamma delta infinity. It is also a game in normal form. It's also called sometimes super game. So I will formulate two theorems about this super game. One about their Nash equilibria and the other about their subgame perfect equilibria, theorem 538 and theorem 541. So the next theorem 538 about Nash equilibria is also called sometimes the Folk theorem, because for many years it was known to the specialists, but nobody cared to write it down and publish it. So, and this Folk theorem contains the very disappointing fact that there are so many Nash equilibria that the utility values form a usually big convex set in R up to M. We will see two examples soon. And even more disappointing, also the strategy combinations which realize these Nash equilibria are not satisfying. They are grim. That means after one deviation from cooperation from some person, this person is punished for all infinitely many following periods. So this is not realistic, as this might also be bad for other players. Nevertheless, there are such strategy combinations which are Nash equilibria. So the second disappointing fact can be remedied. So the problem with the grim strategies can be remedied, namely with the notion of subgame perfect equilibria. They do not allow that the punishment of one player is also bad for the other players. Subgame perfect equilibria usually have a finite punishment phase for some player, not an infinite one. But theorem 541 about subgame perfect equilibria also contains the same disappointing fact that there are so many subgame perfect equilibria that the utility values form a usually big convex set in R up to M. Sometimes also theorem 541 is called Folk theorem, but contrary to the theorem 538, it has known authors. In fact, there are several versions, and two of them are cited in theorem 541. The weaker and older version A is due to Friedman from 1971. It is cited in the book of Holler and Illing on game theory, and also in a lecture course of Mike Felgenhauer, who was in Mannheim almost 10 years ago. And the stronger and younger version is due to Fudenberg and Maskin. They have one version from 86 and an even better one from 91. And I did study these two papers together with a master student. And this version is cited in the game theory book of the three Spanish authors. There Friedman is not cited, but a lot of credit is given to two old papers by Aumann-Shepley and Rubinstein. Both are from 76, but both have been published only in the 90s at some time. So I also studied these papers with some students, with bachelor students. Rubinstein's paper is clean, but it contains a rather weak version. And the paper of Aumann-Shepley contains an interesting version, but also surprisingly bad mistakes. Although Aumann received the Nobel Prize 2005 and Shepley received it 2012, this paper has really severe bad mistakes. One of the many mistakes is as following, or the points of critique is the following on. They use some average utility and take a limit for the number of periods going to infinity, and it's not clear whether this limit exists. If these partial payments in the different periods jump too much or jump for longer and longer periods, it's not clear whether one has a limit. And they claim that they can solve this problem, but they refuse to do it in the paper. So the paper is technically not clean. Anyway, we have the clean version of Fudenberg and Maskin, which I will cite in theorem 541b. So now I come to theorem 538. The Folk theorem on Nash equilibria for infinitely often repeated games. So we start with a game gamma in normal form. which additionally shall satisfy this assumption compact plus continuous, which I had formulated in definition 533e. It said that the set space S of strategy combinations must be compact and the utility function U on it must be continuous. So recall that, for example, a finite set S is automatically compact and their continuity is an empty condition, so U can be then an arbitrary function on this finite set. So in definition 533 we had also defined the values Ui min max. I have recalled this definition here above the theorem in my handwritten notes. So it arises in the following situation: if the player I can choose his strategy after the other players, and if the others want to punish him as strong as they can, then they know that he will choose a best possible strategy to get the maximum, and they foresee this, so they will choose their strategy combination such that this maximum is minimized. So this value is then the min-max value of the utility function. And because of this assumption compact and continuous, this is realized by some strategy combination. So now having this value, now one can define some subset F bigger min-max of the domain of possible utility values. So this is a space R up to M. And this domain is the intersection of two sets. The first one is the convex hull of the utility values of the strategy combinations, convex hull of U of S. And the second one is the open quadrant whose left lower corner is this utility vector U1 min max until UM min max. In a moment you will see two examples. So, and yeah, usually this is a big convex subset of R up to M. So now this is all hypothesis of the theorem. Now I come to the conclusion. For any such value, so in such a value is a value U in R up to M, a vector value in R up to M is called feasible if it's in the convex hull of the utility values of the strategy combinations, and it's called individually rational if for any player Ui is bigger than the min-max value. So now, so that means U is in F bigger min-max if and only if it's feasible and individually rational. So now consider such a value which is feasible and individually rationally, so it's in F bigger min-max. Then the theorem says that there exists a discount rate delta 0 between 0 and 1, such that for any discount rate delta between delta 0 and 1, the infinite repetition of the game gamma with discount rate delta has a Nash equilibrium sigma with this given utility value U. So this is a precise theorem, and we will see first some examples, and we will also see by the examples we see why this can realize cooperation. So now I go to the examples. So the first example is the one of Mike Felgenhauer, example 535, where we discussed the two-period repetition in example 535, and here the U min-max value is 1, 1. And now I go back to this example to show you why the min-max value is 1, 1. Here. So first, player, suppose now that I is equal to 1. And player 1 wants to maximize his utility. So he compares 2, 3, 4, and the best one is. So here, if the player 2 plays L, his best value is 4. If player 2 plays M, his best value is 6. If player 2 plays R, his best value is 1. And the minimum of these three values is 1. So this is the min-max value of player 1 is 1. Now if now I is equal to player 2, he sees if player 1 plays O, his best value is 1. If player 1 plays M, his best value is 5. And if player 1 plays U, his best value is 4. And the minimum of these is 1. So this is a min-max value for player 2. Oops, my handwriting is very bad on the iPad. So therefore, the min-max vector is 1, 1 in this case. And we also see here the values 0, 0, 1, 0, 2, 0, 1, 1, 3, 3, 4, 4, 5, 5, 6, 1. You have to recall them because next we see them on the real plane, on the plane of utility vectors. So this is now the left picture. So we have here these the thick dots are these values. Here 0, 0, 1, 0, 1, 2, 0, 0, 1, 0, 2, 0, 1, 1, 3, 3, 4, 4, 5, 5, 6, 1. And 1, 1 is also this min-max value. So on one side we have here the convex hull of these values. This doesn't work, this is wrong. Oops. And on the other side we have here the open quadrant whose left lower corner is the value 1, 1. So then this is this region here. So together we then get here this region F min max, where here it's open and here it contains a boundary, but here not. On here downstairs not. And you see the values of the best Nash equilibria for the old game is here 4, 4. So all the values here which are beyond 4, 4, they are some result of cooperation, especially the values here upstairs. They are good cooperation. So here cooperation is possible. We get Nash equilibria of these infinitely often repeated games whose values are bigger than the Nash equilibria of the old game. Cooperation is possible in this game. So the second game is the prisoner's dilemma, and again the min-max value here is this value -7, -7, and you recall the table of the prisoner's dilemma from the second lecture in this semester. And I will not go again into this table, but here the min-max value is 7, 7 for both players. So the open quadrant starts here at 7, 7. It's the left lower corner of it. And we have these values -7, -7, -1, -9, -9, -1, and -3, -3. So, and the intersection is in this region here. Which is open here, and here it is closed. So, and again, we see that the only Nash equilibrium of the old game is here at -7, -7. And here we see a lot of values which are possible for Nash equilibria, all the values here. And they all give cooperation. So we have a lot of Nash equilibria whose utility values for both players are better than -7, -7. So here also in the infinitely often repeated prisoner's dilemma, cooperation is possible. That may be also some solution or some good remark for the old prisoner's dilemma. In an infinite repetition of the prisoner's dilemma, cooperation is possible, and one can arrive even at this value -3, -3. So this is good news. And now I come to the proof of the theorem 538. But first I will give the proof for the special case. So where there's some assumption holds. So now suppose we have given a vector which is feasible and individually rationally. So it is in F bigger min-max. And now I will first carry out the proof in the special case where some additional assumption holds. Namely, I assume that we have a strategy combination of the old game whose utility value is precisely equal to U. So this is a strong assumption. It doesn't always hold. In the games here, for example, maybe a clear this first before I talk. Here in the game of Mike Felgenhauer, it is here the value 3, 3, 4, 4, and 5, 5. They come from strategy combinations of the old game. This value here is not allowed because it's on the boundary, and we have to consider here the open quadrant. And here the only allowed value is then -3, -3. We have a strategy combination which gives this value. So it is a rather strong additional assumption, but still it makes sense and to consider the proof first for this assumption here. So, and now I go through the proof under this assumption, and by my hypothesis compact and continuous, I can choose a strategy combination S in bracket I in S, such that its utility value is the mean max value of player I, and I have to add something which I forgot, so it is a correction. I have to add the condition that player I cannot improve his utility value if the other players play their part of the strategy combination. So we have the strategy combination SI here, and suppose the other players play their part of the strategy combination, then player I, the best what player I can reach is exactly this mean max value. So I need this additionally. This equation here doesn't say it. It's not alone. It's not good enough. So I need this additional hypothesis here. So player I cannot get anything better if the other players play their part of the strategy combination. So now I will choose my discount rate delta 0 quite close to 1, and I will choose it in the following, such that the following inequality holds. I want that for any player I and any discount rate delta bigger or equal delta 0, the following inequality holds. On the left-hand side, I have the difference of the utility value ui minus delta times ui min max. And yeah, this is positive because delta is smaller 1 and ui is bigger than ui min max. So the left-hand side is positive. And the right-hand side is positive as well, but the left-hand side is almost fixed if delta goes to 1 and it stays positive, it doesn't go to 0. So this is bounded away from 0, the left-hand side here. And the right-hand side here, this is also positive bounded finite fixed number. And here 1 minus delta can become arbitrarily small if delta is close to 1. So if delta 0 is sufficiently close to 1, this part here is very small, and then this inequality works. So that tells us that we can find such a delta 0, such that this inequality here holds. So this works. Now, the claim for any delta bigger or equal this, the value delta 0, the following strategy combination is a Nash equilibrium, and its utility value is precisely the value u. So the strategies are called sigma tilde I. So sigma tilde I is defined as follows. At each player I plays the strategy with the strategy of the original game with a given value u. And let's recall this here. So this we have the assumption we have the strategy combination S lower index u in brackets, such that the utility value is exactly equal to u. This was a special assumption. So in player I plays his part of this strategy combination as long as no deviation from it of any single other player takes place. So deviations from in one period from several players together are ignored here. So, but if at some period a deviation of a single other player takes place, then from then on, for all resting periods, forever, player I plays his part of the punishing strategy as J in square brackets. So the strategy as J in square combination as J in square brackets is a punishing strategy combination for player J. So and then, yeah. You see, this is obviously a Grimm strategy combination. If one player deviates at some point from this cooperation given by this strategy SU, so this is here cooperation, then from then on all the other players are supposed to play the punishing strategy combination SJ, even if it hurts themselves. So this is just Nash equilibrium. So now I will prove that this is really a Nash equilibrium of this infinite often repeated game. So if every player plays following the strategy, nobody will ever deviate, and in each period the players will play the strategy combination, the cooperation strategy combination SU, S lower U. So that means that the beta of sigma tilde is the tuple of this strategy combinations SU for all periods. It's given here. So, and then the utility value of this infinitely often repeated game, that is this, this factor 1 minus delta times this geometric series times the utility values of SU. But this value now is constant, it's equal to U. And then we have here the geometric series, whose value is 1 over the 1 divided by 1 minus delta. And this here is then U. And then we arrive at the value U here. So this is fine. So if everybody plays always the same, if they all play always the same strategy combination, then it's quite easy to see that we get exactly this value U here. So now, but of course the more serious point is now to see why this is a Nash equilibrium. So is it advantageous for player J to deviate from his strategy sigma tilde J if all other players play their strategy sigma tilde I? And that's not the crucial point. No, I claim no, it's not. If he deviates at some period T0, then his utility can be estimated as follows. His utility is not really is, it can be estimated as follows. So until period T0 minus 1, everybody plays according to the cooperation strategy combination. And then we get here this first part of this, these values here. We have this factor is the factor, this is the fixed factor, and we first get for the first T0 minus 1 period, we get this part here. Then in the period T0, we still have this factor here, the player J can get a very good utility if he chooses now a good strategy for himself. Then this value here can be quite high. But afterwards, in the final infinity, in the all periods afterwards, one cannot see it, the other players will play their part of the punishing strategy combination, which is, one cannot see it here. I write it here, U J of S of J. So they will play their part of the punishing strategy combination as J in square brackets. And the best what player J can do is also follow this thing because it gives him the maximum. That's what I here corrected here. You see here. Here I now need this correction which I had written down here. He cannot do anything better than also for this punishing strategy. And then he gets the min-max value, Uj min-max. So now I calculate these things. Here this value is constant, it's equal to Uj. And then this series here, this is a finite part of a geometric series, it gives this value here. Then this is kept as it is. And here I take out the power delta up to T0. And then I have this constant value Uj min max. And the geometric series here gives 1 over 1 minus delta. So now I erase again all these parts here. Okay. So this is the second line, and now I still can continue to calculate this. Here 1 minus delta and 1 minus delta, they get cancelled, and here also. And here 1 minus delta is then in the middle term, it's then introduced. And I can take out uj here, and then I have delta up to t0 minus 1 times minus uj, which is here. And I have delta up to t0 up to minus 1 times this uj period of t0 times 1 minus delta. And here I have also still, I can take out delta up to t0 minus 1 times delta times uj min max. So maybe it's better if you do the calculations yourself. So anyway, I come to the sum which you see in the second to last row here. I come to this value. And here you say we have first uj and then delta up to t0 minus 1, this times this term in square brackets here. And this is positive by our choice of the discount rate delta 0 and the delta. So this is positive. No, this is negative, what I'm saying. So let's go up. Here we had this inequality here. And if you compare now, then yes, we have put the left-hand side to the right-hand side. And then this whole sum here is negative. So this is uj of the period t0 here. He may choose it as uj of period t0, the best possible value which he can reach there. And this times 1 minus delta minus the terms on the left-hand side is a negative. And that's what we need here. So the part in square brackets is negative. So this is smaller than 0. And therefore the whole thing is smaller than uj. And therefore he cannot win anything if he follows the strategy of the Nash equilibrium. Then he gets uj, and if he doesn't follow it, he gets less than uj. Therefore, this sigma tilde is a Nash equilibrium, and the proof for the special case is finished. But recall now that I had made this very strong assumption, and now I have to give the general proof, but I will do it in the video after the next video. In the next video, I will show you a lemma, which will be helpful for the more technical proof in general case. And afterwards, in the video afterwards, I will come back to the proof for the general case. And this video closes now, and thank you very much for your attention.